So what are you guys?
We're the Smartwood family.
Now you may wonder why I put this in a different section. It's because, believe it or not, since we have the idea of permutations down, we're going to use that to get to our next topic. Okay? But in order to do that, why don't we just start off with some problems and see if we can work our way there. Okay? Let's start off with something like this. Okay, so here's well, pretend it's a word. We don't actually care if they're real words. We'll just call an arrangement of letters a word. In fact, before we do that, why don't we start off with this? A, B, C, Z. Okay, so if I start off with the letters here, the question would be, how many ways can I arrange these letters from left to right? But you know that there are 4 different distinguishable letters. So that should be 4 choices for the leftmost guy, 3 for the next guy, 2 for the next guy, 1 for the next guy, and that would be 4 factorial. So that's just like the problems we've been doing, right? Okay, but now let's look at this guy. So I think in our first attempt, I would say this is 4 factorial, okay? So there are 4 factorial ways of arranging these guys if I could tell the A's apart. If there are 4 distinguishable guys, let's call this one A1 and A2, okay? Or let's make it happier. Well, let's call this guy maybe A smiley and A frowny. Do you agree that if you could tell all 4 guys apart, it's just like the problem on the right, there are 4 factorial ways of arranging those different letters, okay? Okay. Now imagine that you have a particular arrangement. So imagine you have A, B, C, A. Another one might be A, B, C, A, C, B, A, stuff like that. But imagine this is our arrangement, okay? Remember, you can tell the 2 A's apart, okay? All right, but here's my claim. Let's look at this guy versus this guy. The way we've counted with 4 factorial, we've counted these 2 as different cases, right? Because you can tell A smiley from A frowny. Does everybody agree? Okay, but if you take away those labels and you really literally had 2 A's that are indistinguishable, now you have this problem because now when you look at this and this are exactly the same. But do you agree that for any configuration you have, like this with these letters, right? The way we've counted, we pretended we could distinguish A smiley from A frowny. But in every single situation, we've overcounted. Because the truth is, you can't tell A smiley from A frowny, because in the original problem, you just have 2 A's, right? Okay, so how do you fix that? Well, imagine I have a bunch of tables. And imagine at each table, I have 2 chairs. Okay? And let's say I want to count the number of tables. Well, obviously, you just count 1, 2, 3, 4, 5. But let's say for whatever reason, I accidentally counted the number of chairs. So I counted 2, 4, 6, 8, 10. So I count 10 chairs. But I don't want the chairs, I want the tables, right? But you know how to fix that, right? So literally you can see in the setup, right? If we count the number of chairs, we have overcounted. And what we've done is, since each table has 2 chairs, we've double counted everything. So if I said there were 10 chairs, you know that you'd have to divide by the overcount, 2 per table, right? To get the actual number of tables, okay? And that principle just works in general. So for example, if I had 3 chairs at each table and I counted 15 chairs, then that wouldn't be the number of tables because each table has 3, right? So 15 divided by 3 would get me the number of tables, okay? That's the idea. So we're gonna do that. So if you overcount, you know instinctively what you do is you divide out by the overcount to fix it. Same thing. So here, in every scenario we can think of, we've overcounted twice because you have A smiley and A frowny or A frowny and A smiley in every single situation. So what we did was we got 4 factorial, but in every scenario we thought of, we've overcounted twice, just like counting 2 chairs for every table. So to fix that, we divide by 2, okay? Now to get the pattern, do you agree? It's really 2, here and here, right? But you can also think of it as, you got these slots, you have A smiley and A frowny. How many choices for the leftmost guy? 2 of them, right? Either A smiley or A frowny. Once you pick one, how many choices over here? Just 1. So even though it is 2 here and here, you can also think of that as 2 factorial, okay? And the reason why is we're going for a general pattern, and it's easier to do that with factorials rather than just 2, but we'll just see in a sec. But does everybody agree this is now the right answer? Okay, all right, let's do it again. Let's do it now for this word. Okay, I like this answer because we don't have to really count to get the right answer, right? How many different words can you form from the letters in this guy, right? Well, it's got to be 4. Why? Because everything is determined where you place that B. So the B could be here, 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 or here, and that's it. So there are only 4 options, okay? But we're going to try the same strategy. If I have 4 guys and they were distinguishable, then there would be 4 factorial ways. And we'd have A like smiley, A frowny, and maybe A confused, okay? Right, but we've overcounted, right? So we've overcounted in every situation because we pretended like the A's were distinguishable, but they're not. So if we divide by the overcount, once again, we're going to be good, right? Okay, but now the issue is this. Exactly how many ways did you overcount? So let's think of it this way. Let's say we had this particular setup. Okay? All right. And let's say we did have the 3 A's, right? So 3 slots for the 3 A's. How many choices for which A goes over here, if you could tell them apart? There are 3 options. You could pick A smiley, A frowny, or A confused. Once you place one down, how many options are there for the next slot? There's only 2, right? So if we pick, for example, A smiley, this slot can only have A frowny or A confused, right? And once we pick one for this slot, there's only 1 there. You'd have to pick all 3 to know what this looks like. So we're going to multiply. But now you can see clearly that's going to be what? 3 factorial. So to fix this overcount, the overcount is actually 3 factorial. Okay? Now to verify this with numbers, 4 factorial, you know, is 4 times 3 times 2 times 1. Okay? If we had just divided by 3, we would get 8, and then you know that's not right. Okay? But if we do it by 3 factorial, we will get 4, and that's exactly what we're looking for. Okay? Okay, so do you believe that? If you believe that, let's try another one. Let's try my favorite one that I pretty much put in, you know, for the GRE, DAT, GMAT, anything, and that is butt-headed. Okay? All right, so let's do our usual thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 factorial ways if the letters were distinguishable. Okay, so I'm going to start with 11 factorial. So basically we're going to use our what's the general strategy here? Do what you know, right? Even if it messes things up, and then go back and fix the mess ups basically. Okay, so what do? We overcounted. So every time we overcount, we're going to fix it. Remember, there are 11 factorial different setups we could have. That's a buttload. Okay. Okay, so obviously we're not going to write that down. We're going to find a better way of doing this. So let's focus on the repeats. So if we looked at the T's, for example, there are 2 T's, right? There could be T smiley or T frowny. And we already know how to handle that. For every given setup, you could have T smiley and T frowny, or you could flip the positions and do T smiley and T frowny and T smiley, right? Okay, so if that's the case, you've overcounted twice, because you can move those guys around in 2 different positions. But if that's the case, you've overcounted twice. So how do you fix that? You divide by 2 factorial. Okay, but what about, for example, the E's? Again, E smiley, E frowny. So for every given setup, we fixed the T's, no problem, but we're still overcounting because of the E's. And we overcount twice, either this way or that way. So again, we need to divide by 2 factorial. What about the D's? Well, the same thing. We have D1, D2, D3. We can move these guys around 3 factorial ways, like in the previous problem. So we fix that by 3 factorial. So does everybody agree? All we did was count them all up, fix the overcounts one at a time, and now we have the total setup. Not too bad, right? So as a practical problem, can we do this one? So everybody try this out. All right, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 again, right? Super famous problem, of course, because it's M-I, crooked lady, I, crooked lady, I, PPI. I get it, Mississippi. So if you look at this, how many repeats? Well, the I's repeat 4 times, so I think that's 4 factorial to fix them. The S's repeat 1, 2, 3, 4 times again, so I think it's 4 factorial to fix that. And the P's repeat twice, so I think it's 2 factorial to fix that. Is there a general formula for this? Of course, but I mean, I don't know if it's going to help us that much. You take all the letters, right? And then you look at one letter that repeats. And let's say the number of times that guy repeats is R1. So you would divide by R factorial to fix that. And you look at the next guy that repeats, say the S's. That again is 4 factorial, so we'll call that R2 factorial. And the next one that repeats is P, so that would be 2 factorial. So we call that R3 factorial, all the way down, theoretically, right? Till however many you have. Okay. So not too bad, right? Okay. By the way, this guy gets a special name. He's actually the multinomial guy. That's not too bad, right? Okay.